Okay. So for number 1, what is the frequency of the D allele in this population? Well, your little d is going to be your diseased, so it's going to be 1 over your 150,000, and you get 0.00258. And you do 1 over 150,000, and then you take the square root of that because you're trying to find one allele. B, you're trying to find big B, so what you do is you take 150,000 and you subtract it by 1, you get 149,999 divided by 150,000, take the square root of that, and you get 0.997 as your allele frequency. And then for your big D, you just take your 0.997 and you square it. And to find your heterozygous, you take your first answer from A and your second answer from B, and you times those together and you times it by 2, and you get 0.00515. There's the work for that.
So for the second section, the first one, for the IB allele, it's Q. For the IA-IB genotype, it's 2 times P times Q. I'm going from the Hardy-Weinberg equation. For the second number there, so it says that the dominant disorder affects 1 out of 4,000. So that's going to be your Q squared, or your P squared there. It says that 1 in 4,000 individuals in the population affected by this is represented by, so they can be affected either by a homozygous dominant or heterozygous. So it becomes P squared plus 2P times 2 times P times Q is the answer there in terms of the Hardy-Weinberg. For the third question, let's see. So it's asking you about the 3,999 out of 4,000 in regards to that question from above. That equals your Q squared value in the Hardy-Weinberg. For the fourth one, where you have 3 different possible genes or alleles there, you have Q, P, and R. So for the MD allele, it would be represented by the R because it's the least dominant. For the next one, the question refers to the situation presented in the one above. So anybody that has a genotype of the restricted plumage, it's P squared plus 2 times P times Q plus 2 times P times R. Again, just going back to the expanded Hardy-Weinbergs. The human disease HBS is a result of the SNP. Monomorphic is the term that describes a trait that is a single phenotype in 99% of the population. DEAMS is another name for the local population. And major histocompatibility complex gene is a highly polymorphic gene for the last one there. And there's the work for that.
Do you want to go for number 3?
Yeah, so for the third one, it's very similar to the first, except for this is an autosomal dominant. So the big D, anybody that's either homozygous dominant or heterozygous will be affected by the Marfan syndrome. So this is saying that 1 out of 6,000. So the first one, for anybody that's non-diseased, this is going to be anybody that is homozygous recessive. So little d, you take 6,000 minus 1. You get 5,999 over 6,000 is your Q squared value. You square root that, and you get Q equals 0.9999. For the second one, you can take 1 minus your Q value, and it will give you your P value, which is 0.0001. For C, the frequency of heterozygotes, you take your answer from A, multiply by the answer of B, multiply that by 2, and you get an answer of 1.9998 times 10 to the negative 4th will be heterozygous. And then for a population out of 5 million, you take your answer from C, which is the frequency of heterozygotes, multiplied by 5 million. You get roughly 1,000 people. It comes out to be 999.9 people. So about 1,000 will be heterozygous for that. And there's the work for that one in blue.
All right, so for the allele frequencies for this one, you're going to find your total amount, which is 190 of number observed of the different genotypes. You times that by 2 because you're trying to find the allele frequencies. So you get 380, and then you're trying to find your R squared. So you times that by 2, and then from your R squared, R cubed, you take half of that, and you get 22. So you get 270 plus 22, actually plus 44 because you're timesing that one by 2 as well. You get 314 over 380. You take the square root of that, and you get 0.8263 as your R allele frequency. For your R cubed, you're going to do the same thing, except this time you're going to times your R cubed, which has 11 observed, times 2. You get 22. And then you take half of your R squared, R cubed, and you times that by 2, and you get 44. So 44 plus 22 is 66 over 380. Take the square root of that, and you get 0.1737 for your R cubed allele. To find your chi-squared, we were both confused on this, but I think we got it. So you take your allele frequency for R squared, which is 0.8263, like we said before. You times that by the number of observed genotypes for R squared, you get 190. So you go 0.826 squared times 190, and you get 130. And then you take your heterozygous, you get 0.826 times your 0.1737 from, again, A, and you times that by 2, and you times that by 190, the number observed, and you get 55. The third part of your chi-squared, you take your 0.1737 for your R cubed, and you square that to get your R cubed genotype. You times that by 190, and you get 6. And then, as you can see here, you just do it like a regular chi-squared. And you take your 135 minus 130, you divide it by 130, and you square it. And you add those all together, and your chi-squared is going to be 6.552. And it's not a Hardy-Weinberg equilibrium, and it's probably because the R squared circums the R cubed allele. I can go over this one.
Okay.
What is the frequency of CH, CH, and CBC and CC genotypes? For A, you square each of the alleles that you find to get your genotypes, and you get 0.1369, you get 0.0375, and you get 0.0225.
This one, don't you take, once you do the frequency of CB times the frequency of C times 2, going back to your expanded Hardy-Weinberg, because you'd have
Which
P,
one?
Q, R, and let's say S. And so since it's a heterozygous, it's not a homozygous, you can't just square the value. So this would, just like you have before where you have P squared plus 2PQ plus Q squared.
Mm-hmm.
The middle one's a heterozygous, it's 2 times the 2 alleles multiplied together, so you do the same here. So you do the frequency of the CB.
This one's like the fur coat, though. So everyone that's CBC is still going to be CB no matter what. So it's not a heterozygous.
Yeah, but this is asking for genotypes still. So if we were doing phenotypes, you could.
I get
but
what you're saying.
where it's it's the genotype here. Because really, what this would end up being is you'd have P squared plus 2PQ.
Hold on, let me just make sure that's exactly what I did. 10625. So just squaring that would be 0.0625. But I did something else right here.
Oh, okay. Because I got 0.075 as the frequency of the CBC of the heterozygote there.
So you get CBC, you get 0.25
times 0.15, right?
times 0.15
Times 2.
0.25 times 0.15 times 2.
Yeah.
0.075.
And shouldn't that be your frequency of the CBCs?
Just try one thing. Five squared times 2. No. Where did I get that number?
Where did you get 0.0375?
75. Trying to figure out where I got that from.
Because even if you figure here, if you get rid of these two, because you're not dealing with any of those, the Hardy-Weinberg between the two of those would just be R squared plus 2RS plus S squared.
Yeah.
This would be the CBCB, this would be CC, this would be your CBC. And so you just have those two values together multiplied by 2, which would give you that 0.075.
Okay.
I'm going to say that your pen died and you actually freaked out, and that's just an error. I'm
All
going to
right.
say that's not a 3 for you.
All right. 0.075 for CBC. For B, among a population of 2,000 dogs, how many would you expect to be pale gray phenotype, yet be heterozygous? So pale was your CB, so 0.25 times your 0.15, and you times that by 2,000, and you get 150 dogs. For C, you got white coat and
Dark eyes.
dark eyes.
So the CB or CD. It's your CDs here. But then it's heterozygous. So the CD, CB, and CDC added together.
Okay, so 0.23 times 0.25
Yep.
times 2 times 5,000, and you should get 920 dogs.
Yep. Because you do that twice.
Yeah.
And you add the two sums. Yep.
Yeah.
And then D.
And then D, among the population of 15,000 dogs, how many would you expect to be CCH, CB, or CC genotype? So that the OR automatically means you add the two. And so you get 0.37 times 0.25 times 2, and you get 2,775. And then your CC is just going to be your 0.15 squared, and you get 337.5. You add those two together, and you get 3,102.5. And there's the work for that. And yeah, that's 1 through 5. Thanks for watching.